So let's start this second part. I mean, we have been asked by some of you to go to more advanced part of the code, so we will do that. So regarding the regressions, the part that was planned to be discussed now, we will go through that very quickly. So the idea is that I mean, if we think about what we did earlier, in particular at the beginning, is that we attempted to do a classification. So something very similar to what you can do from the statistical point of view with a logistic function. So basically with a logistic regression. So you have data that have a binary output, and you try to teach a neuron to approximate it. Of course, we can do something similar, not for the case of classification, but for the case of a regression. So in the case in which the nature of the data is not discrete, so the output is not 0, 1, high, low, or true or false, but the range of the output is continuous. For example, we have data that are like those represented in this case. Now, for each input that is represented by the x value, the x0 value, you have an output that it's y and it's continuous with a range between minus something and plus something. The idea is that can a neuron learn this kind of relationship from the data? And the answer, of course, is yes. And for that, we need to use something that is extremely similar to what we did before. What is the difference? The only difference in this case is the activation function. Before, we need something that was introducing nonlinearity by transforming the activation potential into a digit, 0, 1. In this case, we don't even need to do that, because basically, to approximate this function, since it's a linear function, we don't need a nonlinear activation. So from the coding point of view, we can use the same function that we wrote before for the classification, but removing the logical function that was comparing the output with 0. And if we apply this and we do the same training that we did before with the same updates of the weights, we will be able to basically fit to do a linear regression of this curve. And once we learn this, we can, of course, apply the same criterion, the same modifications to the more complex network that we built before, and change the activation layers in order to reproduce results that are now continuous. There is something to keep in mind. I mean, here we have only one activation function because this is one neuron. So the only thing that we need to change is that activation function. If we have more complex networks like the one that we saw before, in which we can have layers composed of different neurons, the only activation that we really need to change is the last one, the one that produces the output. So there is still nonlinearity within the network. The weights are still updated, and they use activation functions that can be reload, that can be sigmoids, that can be whatever you want. But since you want an output to be continuous, you cannot put as a final activation function something that produces some discretization. You need to put at this stage something that is either linear or at least partly linear. I mean, we will not repeat the same examples just by changing the data, but in principle, we can do that, and in the book we do. So we do most of the steps that we discussed this morning, a few hours ago, but now with data that look like this, either in 1 or 2 dimensions. In 2 dimensions, basically, we still have input with this bidimensional, and the output now is not 0 or 1, but it's some number that varies continuously in a range. Instead of doing that, let's see directly an application of this approach. So an application of a regression problem, so a problem in which, based on data, you want to learn some complex function that describes something. And we do something that is very physical, because the example that we described in this chapter is related to optical trapping. So basically, we want to emulate the physical system that describes the trapping of the electric particles with a laser in a liquid environment. For that, of course, I mean, we are using an approach that is based on data. It's data-driven, and basically, of at least of some of the data that we use to learn the approximation, we need to know everything. We need to know the ground truth. So one way to do this in the case of a physical system like the one that we will describe is to rely on simulations. So basically what we can have simulations that are based on geometric optics that describe how forces acting on a particle with a specific refraction index vary when the position of the particle varies respect to the position of the laser beam. Imagine that you have a laser beam that is going through the vertical axis of your microscope, and it's strongly focused at some point. You have a particle that is moving around it. This particle, depending on the relative position with the center of the beam, will experience different forces, and that it's relatively easy to simulate. And then you can use those simulations to train a network. For example, a dense neural network like one that we saw before. What will be the input and output of this network? One can think of the position of the particle in 3D, X, Y, and Z, and the output will be the forces in that position. So the three components of the force vector in that specific point. If you have enough simulations based on different particles, different position, and so on, the point is to try to reconstruct the behavior of this force. I mean, this is, from the physical point of view, it's a relatively simple problem. So besides the simulations, we also have a theory. So in this case, we can use as training data the simulations that, as we will see, have some limitations because they are based on geometrical optics, so those are not perfect. They can have some artifact. But then we can use as a test to see how much the network learned the theory, which should not have these artifacts. It does not have these artifacts. First of all, we will use a dataset. I mean, for this part, since the code, the final code that reproduces these examples is on GitHub, you are welcome to download it and run it. We can run it step by step while I describe it, or you can do it afterward as you wish. But basically, you will be able to train while we speak because it's relatively quick. So the dataset is based on these simulations. And this is basically based on a publication, so on a paper that's been published not long ago, I guess I remember the year, but not long ago, in 2022 maybe. So we have within the DeepTrack AI organization on GitHub, we have specific repositories with the dataset that we use in the book. So in order to reproduce these examples, you can simply run this code and you will download that specific data that are needed for this. And basically, once we have downloaded this data, you can organize them using this part of the code. So this is the part that I showed before is loading the part of the data relative to the simulations. This is instead the file within the one that you downloaded that it's related to the theory. See it here. The name of the file tells you that this is the position of the force in the z direction with respect to the z position based on theoretical calculation. You can check how many data points we have and so on. And then from here, we instead load, I mean, once we have downloaded everything from here, with this code, we can download the data relative to the simulations that are contained in these two files. Those are NPI files, are Python files. And in this case, what do we get? I mean, for this, we extract only the position in the Z of the simulation, but the full simulation file contains all the volume or the information about all the volumes, also the coordinates in X and Y. And same for the force. We have the information about the direction of the force vector in the three directions, but in this case, we only extract those relative to the Z component. And what's the reason of that? The reason is that we want to plot and compare these two files. Again, we can check that we have the expected number of elements in our vectors, and then we can run these few lines of code, which basically we do the plots. No, we do the plots of the geometric optics simulations, and the theoretical one. We make it a bit fancy, adding some fonts and labeling. And then we should get something like this. So far, we're just describing the data set that we will use. And we will see that we will use the gray curve, which is the geometric optics simulations for the training. These are also the data that corresponds to the center position of the laser beam in the plane x and y equal to 0 along the vertical directions. And for each z position, so this basically is the focusing. How far away you are from the focus of for the focal plane, in either below or above the focal plane, you see the value of the force. Oh, and you see that the force, I mean, depending on the distance, it changes the direction. It's attractive or repulsive, depending on where it goes. We also see another thing. I mean, this is something that I mentioned before. If we look at the simulations, there are these jumps. What are these jumps due to? This is an artifact because basically the theory predicts a very smooth curve, whereas the simulation has this jumpy behavior, which is also not. I mean, it has some regularity, but it's not something extremely regular. What can originate that? Do you know how geometric optics simulation is done? Basically, you have a volume that represents your sphere, your object, your bead, and then you simulate a number of rays, but it's a finite number of rays. So you have some discretization. When the particle moves, it might miss some of the beams. So you have a region in which the force can change just because you are not using the same number of beams entering into the bead as in the simulation that when the bead was displaced. So this is not something real. It's not something that happens in real life. It's just a limitation of the simulation system, which is something that you don't really want. But let's suppose that this is what we have. And based on this data, we want to train our neural network. So we need to, so we have the data in the format that we have downloaded, and we want to modify them in order to be usable by the network in a similar way what we did before. So we can first write a utility function just to read this data. I mean, I will not go through the details. It's something extremely basic, but basically we need this to organize the data in the way that we will need later. I mean, if we have time, we can spend some time on it later on. But basically, once we run this function on the file in which we store this data, the data vector should look like this. And we see that we have 1, 2, 3, 4, 5, 6, 7, 8 array, 3, 6, 8 elements in each data point of these files, the way we have built it. What do they correspond to? So the first one, it's the radius of the bead that has been simulated. So this corresponds to a bead of 1 micron radius. The second one is the refractive index of the material that's composing the bead. Then the other data that we have, if I remember correctly, corresponds to the force and the position of the particle, or the other way around, the position and the force of the particle. So this is basically the center of the particle respect to the center of the laser beam. And this is the three component of the first vector that the bead is experiencing that position. And we have one of these for each of the simulations, for each of the data point. Okay. At this point, what do we want to do? So we want to use part of the information contained in this data file for the training. So we want the input to be the position. Given the position, the network has to predict the force. So the force is the output. And the force that we have in the simulation file is our ground truth. because basically the network is going to make a prediction, and we want to compare this prediction with the value that is stored in these files. For the last three elements of each, this is moving a bit. Okay, let's see. This is better. So we want to compare it with the last three elements of the vector that we saw before. So for doing that, we have to split the information contained in each of these rows, in each of these elements. And this is what we do here. Basically, we modify the function that we had before and say that basically if we have the elements 3, 4, and 5, remember that Python is zero-based. So the elements from 2 to 4 according to the index of Python, those will correspond to the positions. We multiply them by 1 to the 6 because we had it in meters, and now we want to deal with them in micrometers, which is more handy in terms of the values that we're going to put inside the network. And we do the same for the forces. The forces were in femtonewtons, so the forces were in newtons, so we multiply by 10 to the 15, and we put them back in femtonewtons. So we have numbers with that are easier to deal with. Okay, so for this case, most of the coding, it's about preparing the data. Actually, not only in this case, but in many cases in which you have to use a neural network. Most of the coding that you have to write from scratch is to prepare the data in a proper way for being inputted into the network. Then the network itself, typically, it's something that is partly at least pre-built, and you also only have to change the hyperparameters. But so once we have this, I mean, we can do some check and check how many data points we have, and effectively the number of variables is the correct one. And then there is an important thing that we just briefly mentioned this morning. So you need to use part of the data for the training, but then you also want to make sure that the network is learning properly. And you want to do this in two steps, because first, during the learning process, you want to make sure that everything is going fine. So let's suppose that I have a set with a given number of data that are annotated. So for each of them, I have the ground truth. I want to split them ideally in three groups. One that is used for learning. So the network will learn from that. Another part of the data set, smaller typically than the training part, I will evaluate it during the training just to make sure by plotting some function like the loss function, or by just seeing, by printing the results of the evaluation of the network, that the network is going in the right directions. So that if you have to change something, I don't have to wait until the very end of the training to see how it behaves. And this is called validation. And then there is another part that is called the test set. And this is what I will use at the end. So those are data that the network will never see during training. And I use them just to pretend that I don't know the output. I apply the network on that. Network and see what is the accuracy, for example, in the case of classification, or whatever other parameters and metrics I need for my data set. And this is what we do here. No? Basically, we do here a split of the 80%, in which we take the data, we randomly shuffle them, and divide them in two groups. No? This is referred only on the training data. No? You see, train split 80%. And then we have some data that we use for training and some for validation. And basically, if one contains 80% of the data, the other one contains the 20%. In this case, we're not using the test. We're only splitting into parts, training and validation. Also, I mean, about the definitions. Typically, the datasets are defined, as I said, training, validation, and test. But between test and validation, in some books or in some other or some web page and so on, you can find quite some of mixing. Some people call test validation, or just use the validation for everything and so on. But I mean, probably they should be divided in these three classes, and validation is whatever you evaluate during the training, and test is what you do afterwards when the training is over. But I mean, it's a matter of definition, so it's semantic. Okay, we are at the point of defining the network that we want to use. We're using the same library that I show in the example of the MNIST, so the display. Display, again, is something that we wrote, and it's based on a PyTorch, and it's just something to make your life easier if you want to use some basic or even more advanced architecture. Those are pre-built, and you can just use them, changing the hyperparameters. Not only that, typically in Torch, you have to write the training loop from scratch. Here, we combine display with Lightning, which is another library, and you don't have to write that from scratch. You can just basically, in few lines, define an architecture, run it, evaluate it, do the plots, and the validation if you need it, and so on. So what are we using in this case? We're using, again, a multi-layer perceptron, which is another way of calling a dense network. So we have stack of neurons, piles of neurons stacked up in layers. In this case, we have the number of input features is 3, because the input, remember what we defined, the 3 positions, x, y, and z of a particle, respect to the center of the laser beam. We want to combine these 3 numbers in many possible ways. So the first layer, we have 256 neurons. So these 3 numbers are multiplied for different ways, in many possible ways. And then we get, out of 3 numbers, 256 outputs. Then in turn, are combined together to give again 256, that are combined together to give again 256. And finally, these 256 numbers are combined together again with weights that are learned during the learning process to give 3 outputs, which are the force values, force in x, y, and z, for that specific position. And we compare this prediction with what we got from the geometric optic simulations. So we instantiate the model. We define the loss. In this case, we use the mean absolute error. So basically, the module of the difference between the force predicted and the force ground truth. And here we use a different optimizer. You see that before we used the stochastic gradient descent. Here the algorithm is one of the most popular used in deep learning, which is Adam. Again, we don't have time to go into the details of this. If you're interested, we can talk about it later. So the loss is what we defined earlier, the mean square error, the optimizer is Adams, and then we define something else, which is the matrix. What is the matrix? This is something that the model will calculate during the training, will not use it to optimize, will just show it to give us a hint of how well the training is going. So at every iteration or at every epoch, we will get the print with the value of the mean absolute error that we are using here. So probably before I mixed it up. The loss, what we are using for the optimization in the mean is the mean square error. So it's the force minus the ground truth of the force squared. But at every step, besides this loss, which is what is using by the network to optimize, to learn the weights, the network is also showing the mean absolute error, which is a way to tell us how good is going. I mean, you can print both. Yes, you can print also something else. Imagine that in your specific training, you want some other metrics that is also useful for you to understand how everything is going. You can also print that and can plot it.
Only one thing to add here that could be convenient is that the metrics doesn't have to be differentiable. It can be anything you want that you feel is optimal for evaluating the model performance. There's also an advantage in that sense.
Yes, indeed. Okay. So in the example we discussed before, I briefly told you that we need some way to pass the data to the model, no? For the learning. Depending on the case, you might need some specific way for doing that. And this is one of the cases in which you need something specific. And for that, here we define a specific class that is part of the the dataset class, that it's some class defined by torch, that needs three methods: initialization, length, and get item. Are you familiar with the class? How many of you are familiar with creating a class from scratch and what a method is? And okay, not many. So, Jesus, please jump in, help me.
Yeah. So yes, a few things. Like right now, what we have when it comes to the data is just a vector, right? Which is number of data points times 6. With that, we cannot do much, right? We need to provide this data somehow to the neural network. And the way to do this is by defining a data set, which is a class that contains a set of methods that manages the data somehow. So the init class is what initializes the class, defines the variables and the data inside the data set. So in this case, it receives R, which is the positions, and F, which is the force vector, right? And all what it does is it just assigns R and F to a self variable. Self is a property of the class that can be accessed in any method, as we will see in getItem. So as I said, as Carlo explained before, when we train a neural network, we train it in epochs, right? So an epoch is a full iteration across the data set. But a question I have is, how do you think the torch, in this case, the model knows when it has seen all the data points or when to stop? How do you define the epoch? Do you know? Like you can say 10 epochs, but how does the network knows when it has seen all the data? Exactly, exactly. And that's done with the definition of the len method, right? So len is just a method that tells the data loader, look, this data set has this size. That's all it does, right? So in this case, it just takes length of R. It would be the same doing length of F, because R and F in this case has exactly the same size. Doesn't matter, but so you know. And also the get item is the method that allows the data loader to retrieve information from the data, right? So I, in this case, is just an index, right? So if you just take this data set and you do dataset.getItem parentheses 20, it will just retrieve the position 20 of both R and F, right? That's all it does. So this is what the class does.
So basically, once you have defined this, if you can do something as easy as what you see here. Already, we remember that we already split before the train and validation dataset. No, if now you run geo dataset over the vector, the vector containing the position of the training dataset, comma, the vector containing the force of the training dataset, you are generating a training dataset that now is able to be passed to the network. And the network, since this class has all the methods that we have defined, know what to do with it.
Like, sorry, if you would pass only the data as it is, raw vectors, then the data loader in this case wouldn't have any mechanism to know how big it is, right? And any mechanism to retrieve the information from the data set itself, right? That's why you need this data set manager to communicate with the data loader in this case.
And when you communicate, when you tell the data loader which data, which are those that come from the dataset to use, you also have to define the batch. So basically, the data loader needs to know how the data are going to be passed to the network at every iteration. And in this case, we're telling, okay, out of all the data that you have in the dataset, use the methods that we have defined to take 124 at every iteration and pass it to the network. So basically, divide all the dataset in chunks of 124 each, and make an iteration with each of them. And when network sees them all, it's an epoch that's completed. And then you can start another epoch. And at each iteration, there is the calculation of the gradients and the backpropagation and the update of the weight and so on. So this brings me to say something about the batch size. Because for what we briefly mentioned before, what is preferable to have? A large batch size, basically seeing most of the data in just one iteration, or a few iterations, or very small batches, like what we started at the beginning, where at each iteration we're passing just one data point. Why something in between? Something that is large enough to show that, for example, if you have 10 classes, you have at least a few elements of each, so that the network can update the gradients based on a sample of the population. But at the same time, you want some stochasticity. So if the batch is too large, you will do just one weight update per epochs, which is too low. So you don't have room for optimizations in that case. So you want something that stays between those two. And of course, another limitation is the size of the GPU that are using, because if the GPU is limiting the batch size. I mean, even if you have an infinite amount of data and you want to use batch that are quite large, at the end, I mean, those are limited by how many of them you can load at the same time on the GPU. So at this point, we are ready to define the trainer. And here is where we define how long the training should run. And this is defined by the number of epochs. So in this case, it's 100. And the other input that we have in the trainer, which is accelerator, is equal to auto, basically is telling if running the training process on the GPU, on the CPU, or whatever is best for the specific machine that you are using. So you can define it specifically. For example, you can put GPU instead of auto, and then if you have a GPU, the training will go there. In most of the systems, if you put auto, it will choose the GPU if it's available. If you have a Mac, there's a lot of issues. Because Mac does not have NVIDIA GPUs. They use these MPS, these metal systems. In principle, that is an accelerator that works quite well, but depending from the situation, we find a lot of issues about, in particular, the management of large tensors. Large tensors are managed by MPS in a way that, in some specific case, is not very reproducible and produces some mistakes. So if you are running something and you want reproducibility and be sure of the results, do it on a GPU that it's NVIDIA or on some Fortnite. I mean, I like the Mac system, but this is a big limitation. And I hope this is not recorded because. Okay. So one thing that, I mean, I said before that in this case, we're also doing this validation. No? Basically, at every epoch, at every iteration, we are storing information about how the process is going. And you want to, for example, print it and have your screen while it trains to show these values, but also in some cases you want to store them in a file. And for that, we can use these loggers utilities that come from Lightning. Lightning is the library that I mentioned before that we're using together with the Play to make everything easier for the final user, for the end user. And basically here, when we call the training, besides defining what I mentioned before, we can also say, okay, print the information that we are collecting through the training in a file. And we're using, in this case, a comma-separated value file, a CSV. So basically, list of numbers and with headers separated by commas. And we're telling here that basically this information needs to be stored every 20 steps. Every 20 iterations, there will information about the losses and the number of epochs and the metrics that are calculated will be printed in this file. And at this point, we are ready to start the fitting, which is basically the actual learning. And we do this here. And you see that with respect to what we did before, since now we are also doing the validation during the training, we do not only need the training data set, the data loader, but also the validation data loader. So basically, the data loaders will send to the trainer two information at the same time. One is used to update the weights, and one only to calculate the metrics, to compare, to see how the everything is proceeding. And everything is going to be filed in this file, saved in this file that is called metrics.csv. Okay. The CSV files can be, I mean, I'm pretty sure you're familiar with it, but it can be loaded, modified, and read by using pandas. It's another very popular library. And this is what we do here. Because basically, after the training, we can read this file with what is written here, separate all the specific information that is stored in that, and use it to generate a plot, which is what we have in here. And here we see that, as the epoch varies, you see the behavior of the loss. So the loss is the function that is used to optimize the weight, that means the square error, and the validation metrics. That is something that we're also only plotting to see how fast the system learns and how well the training behaves. And we see them for the training and for the validations. So for the training and validation, you always expect some difference. Why? Wait, first of all, because they're not the same. They're different. But they are representative of the same data set. But the training data set are those that are used for optimization, and the validation are not. So ideally, you would like them to be identical, because then what does it mean? That the system generalizes perfectly. The system learns some property that is a property not of the specific learning training data set, but the specific of the data set in general. If it learns better on the training with respect to the validation, there is a bit of overfitting. So it's still learning some specific feature that belongs to the training data, but is not generalized. So probably you are training too long, or using too many parameters, or the data set is too small, one of these, or something else.
Just one comment here. Does anyone know why, for some reason, it seems that it performs better in the validation set compared to the training set?
Why it seems that in the validation set is doing slightly better than in the training set. If you see, the curve corresponding to the validation is always slightly below the training one. So it's like underfitting.
No, it's strange that it's worse on the data it's training on than the one it's evaluating on, right? Does anyone know why? It's pretty simple in practice. It's just that you evaluate the training loss during the training, but the evaluation of the validation loss is done afterwards. So it's actually trained slightly longer when you validate it on the validation data set.
So if you want the fair comparison, will be to shift the validation curve a bit in the right direction. Because validation is done at the end of an epoch. Okay, so we can evaluate performances, and basically we do that by plotting the curves that we can generate, because now we have a model that learned, meaning that if we input in that model some positions which are like those that we had at the beginning, like x equal to 0, y equal to 0, varying z, we can reproduce the force curve. And it's very interesting to see that, although we're not using an overly complicated network, although we have quite a few number of parameters inside and hyperparameters and weights, the neural network is matching quite perfectly the theory, although the data from the simulations had those imperfections or have those artifacts. So the network is able to generalize better than the data itself, because it's doing some kind of interpolation.
Yeah, sorry, can I say something? I think this is a really cool example of how just designing the network can get you to the point where you want, right? Because one option you could have had here is just designing a massive neural network that can learn the actual simulation artifacts. This is not what you want. In this case, we have only a 3-layer neural network, which is complex enough to just learn the actual physical behavior and not overfitting the artifacts that you don't want to learn. Right, so it's interesting.
Yes. So, I mean, this is basically all we wanted to tell you about regressions now with these examples. And now I mean, the idea is we anticipate a bit what we were supposed to tell you in the afternoon, so that in the afternoon we have more time to make examples. Those examples are based on, I mean, so far we've seen something that is extremely simple. No? In dense neural network, you have neurons, and all the neural receives the input. But in particular, when you work with images, and I guess that most of you are familiar with, I mean, you do work with images, there is another kind of network that are more powerful. And those are based on the concept of convolution. So we will try to briefly introduce that and see some example on how that work. First in 1D, then in 2D. So, and then we will move on with examples about convolution neural network. So let's consider a signal, meaning like a string of data, like the one that we have in here. No, have a sequence in which I have 0, 2, 0, 2, 0, 2. So basically, these data are alternating 0 and 1. Let's suppose that I want to make some running operation, meaning that I define a small vector, in this case, a vector composed by 2 number 1, take the number 1 twice, divided by 2. So basically 0.5 and 0.5. And I do this following operation, no? Which is basically what this is doing here. I move this small vector, that we can call it kernel or filter, in the first position. So I align it with the first position of the signals. I do the multiplication of each input of each element of the signal with this small number, and then I sum up the results. And that becomes like the first element of a new vector that I'm defining. Let's suppose we do this, no? So we do 0.5 by times 0 plus 0.5 by 2. What do we have as a result? What are we doing in practice? So 0.5 by 0, then 0. 0.5 by 2, that is 1. If I sum them up, I get 1. No? Then I shift of one position and do the same operation. I get, I mean, for how the data are constructed, I get 1 again. And if I do this along the whole vector, I always get 1. What am I doing in practice? It's a running average. It's a running average. Basically, I'm defining a kernel length of 2, and then, by moving this vector, 0.5, 0.5, and multiplying and summing up, I'm dead. So basically, out of this very jumpy signal that will go 0, 2, 0, 2, 0, 2, I get something which is its average, which is always 1. I'm doing some filtering. I mean, because this is removing high frequency features. This is a low pass. And if I change the structure of this vector, can you think of other operations that I can implement? I mean, this is the simple one. I take the average. But what else can I do? For example, I mean, let's do something similar. Instead of having 0.5, 0.5, 1, 1 divided by 2, I have 1 minus 1. What am I doing in that case? I'm doing the derivative. The finite elements derivative. Because I'm seeing that if that is large, I'm getting something large. If that is the values are the same, I'm getting 0. So if something is constant, I'm getting 0 derivative. If something is either changing positively or negative, I'm getting derivative. So, I mean, this, it's a convolution. I'm using a signal. I'm modifying that signal locally using some filters that I define, some kernel that I define, to get something out. So the filter is what is changing the input signal and producing the output signals. And depending on the design of the signals, I can highlight specific features. So this is the basically schematic representation of what we just discussed, no? This is the average that we get. This is another version of the derivative that I mentioned before. I mean, you can make it out of a kernel that has a size 3 instead of 2. So we're putting a 0 in the middle so that you have estimating the derivative in a larger range. No? And in this case, if you see something, you see that here you have something that abruptly changes from 1 to 2, you get 0 before and afterward. But where the change happens, you see the jump. You see that he's highlighting the derivative in this point. I mean, in many cases, I'm sure that you have done a Gaussian kernel smoothing. No, basically in this case, you do some sort of averaging, but in which not all the elements have the same value, but basically you give more weight to the central elements and less to the tails. No. And basically, in this way, you smooth a signal. If a signal that it's very jumpy and very noisy, in this case, you are smoothing it up. This is also an example of a low pass. So you're removing the fluctuation at high frequencies, in which case the frequency can be as high as your sampling rate. Okay, this is in 1D. No? For example, this the different the filter that gives the derivative. In this case, this is called the Sobel filter. But now, let's think about the same in 2D. So far, we've been these strings, these sequences of vectors, no? But we can have an image. An image, I mean, at the end, for what we mentioned this morning, this a few hours ago, is basically a matrix in which each pixel is represented by value. And in a very simple case, you can have an image that is black and white. So you have values that are 0, 1. And if you represent it, it can be something like this. So this image that we use it just as an example purpose, you have four pixels here that are 1, 4, 0, and so on. So basically, this is a checkerboard in which each square can be black or white and has sides of 2 by 2 pixels. And we can do a convolution now in 2D. What does it mean? That we can define a filter. For example, we do the same as we did for the running average, but in this case we need a two-dimensional filter. So we take a small square that is that has a value of 1 in 2 by 2 pixels divided by 4. So again, if you sum it up, you do an average because it's 0.25, 25, 25, 25. And now we have to do the running average in 2 directions. Because I mean, if I have a bidimensional object, and we have to run by rows and by column. And if we do that in this, I mean, this is not in a very efficient way. We will mention afterwards how this can be done efficiently. We have a transformation of the image. And for example, if we start with something like this, we see that by doing this operation, we are reducing the numbers to the average of the area covered by the kernel, by the filter, while we move it around. But besides changing the image, there is another issue here. Can you see it from the image, or can you just imagine it? We are reducing size because, of course, I mean, we can apply the filters only on the area of the image where we have values. So it means that the final size of the transforming image is reduced. So to deal with these situations, we will have to, one solution is to introduce some padding. So basically we say, okay, the part of the image that we need to keep the same size after this transformation, we put like rows and columns with zeros, one with zero padding, or reproducing the same value that we have close by, like using the approximation from the neighborhood of the region. But those are details. I mean, it's important, but they still need details. So images typically are not a single matrix. So the single matrix, we have it in a case of black and white. But if we have colors, images are made by a set of matrices. For example, the typical coding for color is RGB. When you have a matrix of intensity for each pixel in the red, green, and blue. There's also another one. You know what that is? You know why there are two? For printing. Yes, okay, that's for printers, basically. But I mean, the result of the two is the same. Basically, you are combining different colors in layers, in channels, if you want, and those are reproducing the image. Now, when we apply a convolution, so when we imagine that we do the filtering operation that we said before, not the average, to an image that has 3 channels, so which is basically a 3-dimensional matrix, which has the size, number of pixels in the y direction, number of pixels in the x direction, plus number of channels, we typically get just one value. So this operation is already including the same operation done over the channels. So out of an n layers and n channels images, if you do an operation like this, you get 1 pixel value, besides the reduction of the size in x and y that we mentioned before. And this is important because why do we need this operation? Yes. So basically, you reproduce the same kernel 3 times. Yes. Okay, what do we need? I mean, why are we introducing this? Why do you think that this might be interesting to use it in deep learning for image analysis? The convolution, no, like the filtering, convolution in general. To extract some property of the image, but how? What is the key? The type of filter. So exactly, but I mean, so far we have been defining by hand the type of filters. The nice part of using this for image analysis is that the filters can be something that the network learns. So the filters are the weights of an architecture that learns which features it should focus on for a given result. Let's suppose that you have an image and you want to classify, like the classical example that you find everywhere, cats and dogs. There are features of these images that are different, but we don't know which filter, which kernel to use to highlight them. But if we are able to train a network and say, look, use let's say 3x3 kernels, a very large number of those, like 256, and put in a layer, and do convolutions. The convolutions again transform to an image in such a way that at the end you end up with another image that doesn't have any real meaning. It's just a set of numbers in which you want to highlight different features and combine them together to finally give us an output that is 0 if we get a cat and 1 if we get a dog. Then you figure out what are the kernels. I don't know. I want to know. But you can do that. So basically, we're doing something very similar to what we did before for the dense neural network. But we're not using all the pixels simultaneously. We're considering something that is very important in image, that there is local correlation. So basically, the value of pixels in a specific region, in a small region, are somehow related, either because they are similar or because there is a change. And in this way, we are able to impose something that is very important, which is translational invariance, that we didn't have before. Because when we use a dense neural network, you learn that each pixel, it's an input in your dense neural network. So it has a meaning because it's that specific pixel. But in this case, the result is translational invariant. So you just learn local properties and combine them together properly in order to get your results. That depends on the architecture, because basically you can combine together kernels of different sizes, or you can reduce progressively the size of your original image in order that you can collect features at different scales. But inherently, it's not invariant size. I mean, my honest answer is knowledge of the problem and trial and error. So you have an idea on the scale of the features that you're observing, no? For example, if I have a checkerboard that you see it's size 2 by 2 and you want to use all images that are similar to those, I will use a kernel. I will never use a kernel that it's 8 by 8 or 1 by 1, which is not doing anything. I will stay like 3 by 3, 2 by 2, maybe adding 2 layers that progressively reduce the size to see if there is something else that I'm missing, but not changing that. And then the rest is just like trying a bit. The good thing is that you don't have to decide which kernels to use. You just vary the number of kernels. And I mean, one exercise that you can use is given a data set, you train a network and progressively increase the number of layers, number of parameters. And you see if your metrics improve. At a given point, it will not improve or you will start getting overfitting. And probably at that point, you're using too many parameters. I mean, you can do it also in the other direction. Reduces progressively until the accuracy or the metrics that you get makes sense for your task. If you start, if doing some change of number of layers moves you from 0.95 to 0.6, probably you need at least that number of parameters to get a decent result. But it's not something that you can know a priori. I mean, there are for images, in particular for image classification, there are many datasets and there are many competitions that have been benchmarking the best. But I mean, those are for all kind of images that you can find in the internet or in real life. So that includes not only animals, but landscapes and objects of common use and everything. Actually, there's this ImageNet website in which you have different data set of different sites and a different number of categories. I guess that is one of them that has something like 13,000 different categories or something like that. I don't remember exactly the numbers. So the idea is to benchmark your method on those if you want to do something general. If you have something more very specific, what typically one can do? I mean, let's always think about classification. You want to classify images, and are images, for example, of cells from your experiments. Now, there are specific network trained for those. But let's suppose that we don't have them. We can get one of these pre-trained network, pre-trained on all the possible features found on these millions of images that are stored online, not train it again from scratch, like freeze most of the layers, most of the weights, and just change the last few layers and train it again on your problem. So you're still using most of the information collected out of very different images, but then making it more specific for your problem. You reduce, I mean, it's time efficient because you don't have to train on again from scratch on all the possible images. It's data efficient because you can train it specifically on your data set and typically gives nice results. Of course, if your images are something that have some feature that has never been observed in the data set on which the architecture has been trained on, then you have to do something new, something on yourself. There is Optuna that basically change the, I mean, you can tune it in order to change hyperparameters and see which combination of hyperparameters gives you the best loss function or metrics or whatever. So you need an objective.
Yeah, there is a lot of hyperparameter optimization when you build neural networks. I mean, in my experience, most of the time, especially, I mean, of course, you need to follow the heuristics. If you work with images, you want to try first a CNN, probably, right? That's most of the cases. In my experience, when you build a neural network, there is a huge amount of families of neural networks that can map really good your data and can give you optimal results. I think the actual advantages or improvements is when you play with the training strategy, right? Like right now we have a simple supervised like training strategy, but then you have many other different options that you can also try with the same architecture. The choice of augmentations, for example, how you augment the data, how if you rotate the cat, you show, I mean, you train some invariances to the network that it can use to improve even better, right? So, I mean, it's not only about the neural network, but it's just about, you know, a group of possibilities that you can play with.
For example, regarding invariance, no, we said that inherently you have translational invariance with convolutional neural network for the way their convolution is calculated. But if you include augmentations, basically during the train, when the data are passed to the network, you don't pass them always in the same way. You rotate them. So the network can learn rotational invariance, although it's not something that's inherently built into the convolution.
Exactly. Yeah, I think that distinction is actually important because, I mean, with the convolutional neural network, even if you don't train it, you get a translation equivariant, right? Like the feature map without training, just random initialization. If you just move the object, the feature map will also move, right? That's something you get just for free, but it doesn't mean that the network cannot learn invariances just by augmentations and training strategies. For example, the MLP, it doesn't have any spatial correlation, but it doesn't mean that it cannot learn spatial correlations given a fixed field of view. Like it can still learn to relate pixels, even if it doesn't have any mechanism, explicit mechanism. But for doing this, it needs a huge amount of data and training, right? So it's not efficient, but it can still learn something.
For example, if we train the MNIST as we did before, no? On using a dense neural network in which all the numbers are perfectly centered,
Yeah.
It will not recognize a number that is shifted. So you have to have numbers that are slightly shifted in order to train the network for that. But the convolutional neural network doesn't need that because it's already translationally equivariant.
And then maybe just one final comment that in practice, actually, when it comes to the kernel size that you were asking about, you almost never change that. It's either 3, 5, 7, or 9 in almost all practical convolutional networks.
There are a few network classification that switch between 3 and 5. So they have some layers with kernel 3, some layers with kernel 5, but typically it's an odd number. And yeah, the typical range is 3, 5, 7. And I guess
you usually don't. That's not something you change too much usually.
Because a more efficient way to learn at a larger scale is to keep the kernel the same size, but progressively reduce the image. So do downsampling of the image. So most of the architecture in convolutional neural network are progressively reducing the physical size of the image, but increasing the number of channels. So you get more features, but they learn information from progressively larger region, making the image smaller. Sorry? Yeah. Yeah. Okay. So we've been anticipating a lot, but let's go step by step and see what we do in these examples now. So here we can start creating the image that we showed before. So with the checkerboard, and we do it with these few lines of code, and then we can use matplotlib to represent it. No. So the image that we got in this scale is this one. So it's not something that goes between 0 or 1, but it goes, for example, between, in this scale, between -2 and 2. No? And we have dark region and bright region. And now it's, I mean, before in the example, we had 2 by 2 squares. Now this is 4 by 4. And let's see how the operation performed by some filters modify these images. No? And a better way to do the convolution, instead of doing this double for loop in which we run on the multiplication pixel by pixel at each moving along the number of rows and number of columns, it's by using pre-built functions that are part of the torch neural network package that automatically do that. Also because, I mean, if you think about it, I mean, I'm pretty familiar, pretty sure you're familiar with it. So what is the best way of doing a convolution mathematically? So what I have to do is this. I mean, let's consider for 2D. I have this kernel, I have to multiply it point by point by every position into the image, sum it up, and transform, and this way get a new value. How can I do that efficiently? In fast Fourier transform. So from the computational point of view, I can use FFT, a fast Fourier transform. So if I fast Fourier transform the input and the kernel, this operation is just a multiplication, and then I anti-transform, and I get the output. This is property of Fourier transform. Okay, so what do we do here? We create the convolution, basically using this com2d layer, which is part of Torch, in which we define the number of channels in the input. So basically, how many colors has the input image, how many channels, how many output channels we want, and the kernel size. And in this case, it was the kernel size of 1, 3. And in this case, I mean, just for the sake of the example, we don't use the bias. And then we define filters as a tensor of zeros with the size that we see in here. And just we initialize it with that. And then, I mean, we are defining this tensor, that, or at least part of this tensor. So this tensor is made of 4 elements, and we will see in a second why. The one corresponding to the first dimension and the second dimension equal to 0. So the first element in these 2 dimensions is made of 1s divided by 3. So basically, it's doing some sort of averaging. And then we see that the other one, the number 1, element 0, is doing the sober filtering, 1, 0, -1. So what are defining here? Basically, we are putting by hand into the convolution layer with which we can probably build a neural network, 2 specific layers. One that does the average and one that does the derivative. In one direction, not in 2 directions. Because if we see, the dimension of the kernel size is 1 by 3. It's not 3 by 3. And then, basically, we use as these filters that we have defined as weights of the layer that we're defining. So basically, we're creating something that is typically within a convolutional neural network, so something that defines the operation and in which the weights that compose the layers are updated randomly, but putting the layers by hand with a specific design. And then we can plot the results of this operation. And we can see what they do. So basically, we start with the checkerboard that we defined earlier. And we create out of these two new images. One that uses the first filters, the first kernel, that basically does the average in one direction, and the other one that basically calculates the derivative in the same direction. Do you see the effect of those? The first one is clearly an average, but only in one direction, you see? And the second one is highlighting the changes in one direction. So when you have a shift between a dark and a dark checkerboard and a bright one, you have values that are either high or low, if that is increasing or decreasing. So this is just to visually see the effect of this. I mean, this layer is just calculating these values, but we can, since in most of the operation we have to add up some activation. In this case, we use the ReLU, the rectified linear unit, that basically gives 0 if the output of the operation is negative, or the value without any change if that is positive, no? That we saw before. And we see that just by applying the ReLU, this is how it changes. So basically, all the values that were negatives from the operation that we did before, for the filtering we had before, are now set to 0. So if we imagine that we're using these two kernels into a real optimizations, no? Or let's say in a different way, that the network is learning these two kernels to highlight some feature of some images that we are using as a training data set. Whatever creates a negative pixel or a negative feature is not used. So it's not that the network is always using all the weights that are needed. It's only used those that are relevant, those that produce a high activation. The other thing that it's useful is the pooling. What is the pooling? I mean, as we said before, one way to access information at a large scale can come by reducing progressively the size of the image. So let's start with an image that is, for example, 256 by 256. And we know that the relevant scale that we're interested in, it's 3 by 3. So we apply information using a set of kernels that have size 3 by 3. But then at this point, we want to see if there is information also at a larger scale. I mean, one possibility will be to use on the same original image a larger kernel. But another thing that we can do is say, okay, since for getting information at a larger scale, the detail at the smaller scale are not relevant, we can average out or just take the maximum. So we can do something that's average pooling. So out of the image, or the feature that we created from the image, we do not consider every single pixel, but just we consider out of region, let's say, of 3 by 3 pixels, the highest one. So we do max pooling, or we consider the average of those ones. In this way, at every layer, so every time that we apply filters on the image, we progressively reduce the information. And this is very useful. For example, when you want to get from an image to a classification, the classification basically you want to get one number out of it, one that tells you which class the image belongs to. If you have cats and dogs, that is the number that is either 0 or 1. So you can progressively reduce the information while combining it at multiple scales to get the final result. And basically what the pooling does is what I told you before. Basically, you reduce the size of the image, getting either the average of the results that you get from the previous step, or the maximum, or the minimum in some cases that you think that is relevant. But I mean, since we are typically using activation like ReLU, the minimum is not very meaningful. It's more the maximum. That is what is telling us what is going on that for that feature. Imagine, I mean, for applications like classifications, the reduction, the progressive reduction of the sites is very important. But in many applications, you want to, for example, reduce progressively the sites to minimize the number of parameters that describe the image. But then you want to use this fundamental parameter to describe what is really inside the image to recreate the image itself or another version of it. For example, imagine that you want to do some segmentation. You have objects like cells. You're not interested about the intensity of each pixel. You just want to highlight regions where the cells are, with respect to regions in which you have noise. So one possibility is to progressively reduce the image in which you are filtering, if you want. No? You're using some low-pass filtering until you reduce the information about the image to a small set of value, and then use only this small set of values to create the output image. And in this case, it can be something like 0 and 1s corresponding to semantic segmentation of where cells are and where cells are not. In this case, I mean, you need the first part in which you progressively reduce the image. And you can do it, for example, combining convolutions and pooling. But then you also, in the second part, you have to go back to the original sites. So you have to upsample. And one way to upsample is basically, just extend. I mean, you can do it. It can be done in two different ways. Let's see the first one. The first one, you see it here. You just reproduce the same value multiple times. If you have 1 pixel, if you've reduced the image, let's say, to 6 by 6, and you want to amplify it back, then you can use an upsampling of a factor of 2 by 2. So in both directions, you amplify it 2 times, and then you increase the size of the image from 6 by 6 down to 12 by 12. Or if you use a factor that is 3 by 18 by 18, and so on and so forth. And here, for example, we do it with a scale factor of 201. So basically, you upscale only in one direction, and you see that the size of the image only changes in the y direction, but not in the x direction, no? Just to see how it works differently. Well, I mean, we don't show it here, but another way of doing this, I mean, so when for doing this upsampling, you can reproduce exactly the same value multiple times, but you can also do it using some, for example, bilinear approximation or nearest neighbor. So there are different possibilities. The other possibility that is something that can be learned because it's using what is called an inverse convolution. So basically, in that case, you are upsampling, but the kernel that you use for upsampling is learned by the network, and it's also a method that it's useful in some architectures. But the objective at the end is the same: is that scaling up again something that has been squeezed. I guess it might be clearer in some examples that we'll see later. Okay. So let's see now what happens if we combine some of these operations, no? And but now we combine these operations not with specific kernels that we design by hand just for the sake of showing how they work, but putting all this information together sequentially in something that can be learned. So in something that is like already a convolutional neural network. And this is an example of it. So what do we have here? We have two-dimensional convolution, what we mentioned before. So it's something that gets one input channel, so an image that it's grayscale, for example. You only have a matrix of values that have some range. Out of this image, you use a kernel of size 3, and when you use only one parameter, it means 3 by 3, to calculate features. So basically, you vary the number of kernels. You have 16 possible kernels, because then out of these weights that form the kernel pixels, you generate out of one image 16 different channels, or 16 different activation of 16 different features. I mean, the definition of this so channel refers to the input image, because typically to the colors. When this dimension, when is referred to images that have been transformed, is typically called activations or features or feature maps. So basically, the idea is this: what this layer is doing is taking the original image, and out of it creating 16, if you want, copies of it. But each of these copy is manipulated because it's been altered by doing a convolution with a kernel. We have 3x3 kernel, and each kernel is different from the other and produce some results. So highlight some features. Which features? We do not know. Those are going to be learned depending on the final task. After this, we add a rectified linear unit. What does it mean? That each pixel of these activations, if it's negative, is going to set to 0. So we're not going to use it for the other calculation. If it's positive, it's going to pass as is. Then what we do? We do a max pooling with a kernel of size 2 and a stride of size 2. Stride is another parameter that we need to use, because basically, so we started with an image. We don't know the size, but let's suppose that it's 256 by 256. The convolution operation did not alter the size. So the features that are created, the 16 features that are created by the random kernels, by the random filters, have the same size. But now we want to reduce it. And we reduce it taking the maximum value out of each region of 2 by 2 pixels, but then we do not shift it in steps of 1. We shift it in step of 2. Meaning that, we start from pixel 0, 0, 0, 1, 1, 1, 0, 1, 1. We take the maximum of this, and this is going to make the first pixel of the new image. Then we shift this of 2 in the row directions. So it's not that we are doing a running average. We are running average, but running in steps of 2. So we are effectively reducing the size by a factor of 2, which is not the case if we shift with a stride of 1. If we shift with a stride of 1, we reduce it by a size, the initial size minus 1. If we do it in steps of 2, we reduce it by a factor of 2. So basically, at this point, the image is going to be half the size that it was originally. And we apply another convolution. Again, we had 16 channels because the max pooling did not alter the channel structure. So if you want the longitudinal dimension of the image of the features that were created, but out of this creates 32 more. Remember that when the convolution is applied, the convolution is applied simultaneously in the longitudinal directions. So each of the new feature that is created in here comes from the 16 features that were created earlier. And again, we keep the kernel size equal to 3. We apply another activation. So again, values that are negative are set to 0. And then we max pool again, meaning that we take only the maximum of nearby regions of 2 by 2. So we reduce the size of a factor of 2. So the linear size of a factor of 2. So the size of the image is going to scale by a factor of 4 in number of pixels, total number of pixels. So this is a neural network. Basically, we can use this architecture to learn something out of a network. But there is a problem. Let's suppose that we want to use, for example, this for classifications. What we're going to end up with here is still an image, or still a three-dimensional object that has x and y sides and number of features in the longitudinal direction, in the direction of the channels, that is 32. Because the max pooling does not alter that. So if we want to do some calculation or use it for classification, we want to reduce this information further and collapse it into a few numbers or one single number. And let's see how we can do that. So one way to do this is that, so let's suppose, let's just remember what we did. Initial image, 256 by 256, one layer, one channel. We reduce the size to 128 first and then to 64 by 64, but then we increase the number of channels from 1 to what was 32. So now we have an element that's 32 by 32 by 32 elements. Is that correct? So 235, no, 64 by 64 by 32. 64 by 64 because we reduce the image of a factor 2 and then 2 again, but then we increase the number of dimensions. So each of these pixels has information that we want to use to calculate something later on, like a class. How do we combine these numbers together? One possibility is to flatten them. So we suppose that all the correlation at the spatial level were already calculated. So now the number that we end with, these pixels, just have information that we can treat using a dense neural network. So we transform this three-dimensional structure in a unique vector. We flatten it. And all the numbers that we get out of this vector are combined using a dense neural network with a number of layers that is defined in here to give out two features. So at the end, we end up with two numbers. And then on these two numbers, we apply a softmax activation that is giving us either something close to 0 or 1. So we have transformed a structure of an image that had information spatially, first to collect information local using these convolutions twice. Progressively, we have reduced the sites, so we've been capturing at least two different scales, which was the 3x3 scales original defined by the kernel sites. Plus, once we have reduced, again 3x3, but with a reduction of a factor of 2, so with something on a scale that's say approximately 6x6, although that is not a direct calculation. And then we have compiled all the different information together to get up two numbers that will tell us something, for example, about the class of this image. So this is what is called a dense top convolutional neural network, because we have a convolutional base with a dense layer at the end that combines information in order, for example, to classify. And we can see, for example, what are the sizes of the tensor generated at each stage. Okay, so very theoretical so far, very abstract. But can we combine this information into a real case example? Yes. And this is what we're going to quickly see. Let's see what time it is. So we have half an hour, plenty of time. So we can do this to classify cells. Actually, those are blood samples. It's a data set of blood samples that are being classified by experts as either infected or not by malaria. So those are very small images of slightly different sites that can be downloaded again from the GitHub repository that you can see here. And they look like, I mean, we can visualize them using some code, but they look like this. And you can see the ground truth that has been annotated by, I guess, some expert. And you have a few that corresponds to parasitized and have class 0. And in those, you can see that have something that make you suspect that they're parasitized, because you see this feature like this spot in here, also this one here, but it's not crystal clear because there are others that are uninfected. They also see some feature, probably dimmer, but still they have something that looks like this. The idea is, can we use the network that we just described that extract information from these images with a convolution, then combine all the information that's being collected into classes 0 or 1 that tells us if a cell is infected or not, if it's parasitized or uninfected? Let's try. So we need to do some manipulation on the data set as always, no? Because that is probably, as I said before, is probably the most I mean, I don't want to say boring because it can be fun sometimes, but it's a bit mechanical. So we want to transform all the images to have the same size. So we resize them to 28 by 28 pixels and transform them to tensor, because with PyTorch convolutional network, we need to use tensors. We want to get the labels. So if the class is 0, 1, if it's infected or uninfected from the data themselves, and we want to transform this label. We want to reverse it, because originally it's 0 for how is it? It's 0 for uninfected. It's 1 for uninfected and then 0 for parasitized, and we like it the other way around. This makes more sense, no? 0 if something is uninfected, and 0 is like the negative, no? And 1 if it's parasitized. But I mean, this is something that you can skip. It's something, it's just matter of taste and to show you how to do it. So we do it, and then we transform also the label into a tensor, because we need that transformation for that. Then we can use a utility, which is image folder, which is a class basically, that automatically get the image transformed according to the function that we defined earlier. If we define, we just need to tell this class where the images are stored, if they need transformation, and if the target, which in this case is this label 0 or 1, needs some transformation. We have already defined these two functions. So in this way, we are creating the dataset using this class image folder of. What do we need to do at this point? We can define some function to plot them, no? Like the one that we have in here. And just to check that all the transformation that we have done makes sense. So after we do the transformation, we take the dataset, we plot it again, similar to what we did before. We see that now we changed the label because all those that are uninfected are 0. Effectively, all the parasitized ones that now have label equal to 1 have this, most of them at least have this structure or this feature that makes them look like different from the others, and so on. So it seems that our transformation, our manipulation of the data worked. So we need, as always, to split the dataset. In this case, we will not do validation. We will not check on part of the dataset what happens while training. We just split it into two parts. One that is for training and one that we will use afterwards for test. So once the network has presumably learned the weights, we applied it to part of the data that network has never seen, and just to evaluate the performance. We define the loaders, and we can do it automatically. We can do it easily with the function pre-built in Torch. And here we define dense neural network, and we can see if a dense neural network is enough for this task. So we've been talking about convolution a lot of time, but since we want really to highlight how powerful convolution is, let's compare it with something. Let's have a benchmark. And this benchmark is basically similar to what we did before for the MNIST. We just define a dense neural network and we apply it. We do some binary classification as a loss function. We train it. I mean, we don't have time to go through the definition, and we calculate the accuracy. And at some point, we should see that, I mean, we should read, I mean, that if we do this operation, and actually, if we go to the here, let me see. This is chapter 3. If we go to the example here, we can see the notebook that already ran. So you see that is the training that we run offline. And we see, for example, that using only the dense neural network, we get a loss of 0.68, but the accuracy that we calculated is around 63%. So using a dense neural network, what we used this morning for the MNIST, in which you don't use convolution, we don't take into account spatial correlation, produce a result that is okay, but I mean, it's not very different from what you get from a random classification. If you just randomly classify, you get at least 50%. Here you're getting only 10% more. And I mean, if we consider this image of a lot of information, it's not much. So it's not a great result. A dense neural network here alone is not doing much. And we can see that using a matrix. I don't know if you're familiar with the ROC curve. So this is basically a metric that tells you, at varying a threshold, that tells you if a number can be classified as positive or as 0 or 1, or true or false, how many true positive you have respect to how many false positive you get. Ideally, you would like this curve to step up to 1 for very false positive and stay constant to 1 forever. Something that is completely random will get a ROC curve that is basically a straight line with slope equal to 1. So everything that is above a straight line with slope equal to 1, it's better than random, but something that works very well is something that goes up quickly and stays up to 1. This matrix was developed for the detection of enemy airplanes during the Second World War, I guess, from the radar. And that's why the name is receiving operator characteristics. Because basically out of the object that they were seeing of the radar, they wanted to know for sure that there was an enemy, because they wanted to to shut it down, and they don't want to create any instance of friend fire, no, to basically to shot at their own plane. But anyway, so this is the result for this dense network. I mean, one way to evaluate the rock is calculating the area under the curve, which is the value that's reported in here. So area under the curve is also a value that varies between 0 and 1. In this case, we get for an accuracy of 63 approximately an area under the curve of 64%. But now let's introduce the convolutional neural network that we mentioned before. No? So now we have a network that is more complex because there is a convolutional part, what we have there on top, plus the dense top, which is a linear layer or a dense neural network that combines the result of the convolutional neural network to get the final classification. You see, it's I mean, the print of the network is like this. We have 4 convolutional layers, and then we have the dense layers. The number of features is going from 1 because this image is not. Oh no, the image is RGB, so we have an input channels of 3. Then we convert it to 16 feature, then we keep 16, then we double to 32, we keep it on 32, and then we combine everything in this output. And the output, in this case, only 1 feature, because basically, since it's a binary classification, it's enough to know if that value is close to 0 or close to 1 to classify it. What else? We do max pooling. It seems that we do not do max pooling. I see we do max pooling. You see here, we do max pooling here, so we reduce effectively the size with a factor of 2. And yeah, and then we compile it. We run the results. We check the results and see that now, just by doing this change, we got an accuracy of almost 95%. So the convolution alone is able to learn much better what's going on in these images. Because now, before we were able to classify with a 60-something% accuracy, now we are much closer to the 100%. So you see that the ROC curve improved a lot. As I was saying that we should expect in a very nice case, it's going up fast and it's staying pretty close to 1. The area under the curve, which is the integral of this, is also very high, close to 99, meaning that the network is performing very well. But what did the network actually learn? So typically when we speak about deep learning, you always hear about black boxes, no? And one of the things that we mentioned before is that, I mean, these kernels have been optimized with this result in mind, with the result of classifying. But what did they learn? Can we somehow explore the architecture, what the architecture learned and how it got to these results? And there are a few methods that can help us, to interpret the results and make the network less a black box. One, we're going to, let me see what time we have. Yeah, we have 10 minutes, okay. So one is the following. So we can, after the training, we can see specific layers which filter used. And not only that, but we can also learn about the gradients that was used at that step during the maximization. If we combine the value of the weights, the value of the layers with the gradients, can highlight the region that were most relevant to make a decision on a specific image. Let's think about it in a different way. So you remember that when I show you the initial images in which some were parasitized and some other were not, I indicated some features, some like purple spots on the parasitized one that look like, different from the cells that were not infected. Are those the characteristics that that the network learned and highlighted to make a decision? We can see that if we go to a specific layer, plot an average of the specific kernels used for those features, multiplied by the value of the gradient at that point. And this is something that is called GradCam. And I mean, so this, for example, is representing all the layers, for specific layers, all the kernels applied to the image. So we take an original image, we make it go through the network, and then we say, okay, these specific layers, when the sites of the cells have been already reduced, I guess, this is the original sites. Each kernel does this manipulation, these changes to the image. So kernel 1 transform it like that, kernel 2 like this, and so on and so forth. Then we see we have 16 kernels. If we do it at the next layer, when the image has been reduced, you see that the image changes. And now we have not 16 by 32, because as soon as we reduce the image, we also increase the number of features. And we see that this is the effect of each different kernel, of each different filter on the original image. And we can see it before the activation and after the activation. I mean, let me first see if we have an image of the original cell that we're using for this. No, we don't have it here. We'll show it later. But basically, here we have the code to visualize what's going on inside the network, or as a result of the network applied to a specific cell. So can we combine now the information about this activation, these features that we learn with the gradients, and superimpose it to the original image to see what part of the cells was most relevant for making the decision? This is what we do here. And this is basically the original image, the combination of the kernels applied in a specific layer with the gradients, and this is the overlay. So you can try this on many of the parasitized images, and you see that in most of the cases, not all of them, because of course the accuracy is not 100%, it's 90 something, but it's not 100%. The region that was most relevant to decide if a cell was parasitized or not are things like this. So this is in a very simple example, a way to understand what drove the decision of the network to classify that. And it basically is pointing out to these spots. So this is probably a parasite or whatever was needed to the machine to learn that the cell was parasitized. And this method for interpretability is called GradCam, and it's very popular, and it's been developed already quite some time ago. To do this part, there are a few interesting things to learn. One is the hooks. Hooks are basically functions that you can temporarily put into a neural network to get out results at that step. So you have a neural network that is training, but you can include temporarily something that provides you the results while the machine is either doing forward propagation or back propagations. So you put these hooks that calculate something and give you up to the results. Then you run the network, either evaluating or back propagating it, and then you get these results, and then you use it, for example, for creating the GradCam. Basically what you get is the activation during the direct propagation and the gradients during back propagation, and you combine them together to create these maps. It's I mean, the details are described in the notebook and in the book. I mean, unfortunately, we don't have time because that from the informatic point of view, that it's very interesting, and it's it's a tool that it's extremely useful. But that's what we have. So, is there any question? No? Everything clear or nothing clear? One of the possibility, and probably is the main reason, is that these spots that probably are associated with the parasites appear everywhere. So you need a network that, and in their intensity, typically is not different from some other feature of the cell itself. So if you don't introduce something that tells you that there are objects of a specific sites doing something, which is something that you get out of correlation, there's no way to get that. The dense neural network is telling you something, about pixels, all the pixels together, and out of that you get a lot of numbers. But I mean, you need something able to say, if you have a region of pixels close by, no matter where they are, that are high, that is probably a parasite. And that is something that you can easily do with convolution, but it's very hard to get without convolution. So if it's something that has a very high intensity compared to the background, you can still do it with a dense neural network. If there's something that specifically happens in a region or in few regions, you can do that. But it's something that can happen everywhere and does not have a clear change in intensity from the other regions, then you need to get information about shape, size, and so on. Yeah, because I mean, in this case, the feature is clear. Yeah. I mean, yes. Something that I mean, can just think of based on what you say. I mean, I didn't think a lot about this, but let's suppose that we can quantify this. Probably just the total intensity of this tells you on how many parasites or how big the parasites or whatever that is. I mean, if that is a good reporter of infection or the stage of infection, I don't know. But if that is, then probably doing this quantification will give you something along that line. Yeah. And in this case, will be some information that you get in an unsupervised way, because you're just teaching. The machine is just learning parasitized or not. And this is something that you get out of the process, but without imposing that, more parasites is more infected. And if that works, it's great. I don't know if that's going to work, but maybe yes. Sure. Okay, so if there is no further question, I guess it's time for lunch.